Hi everybody, Nirav Mehta here. I'm down in the lab and I've got some students here and we are taking a look at some old oscilloscopes today. So it's gonna be fun.
My name is Angela.
My name is Rioma.
My name is Nathan.
Today we're going to talk about oscilloscopes. So here's some old oscilloscopes that we pulled from the supply closet in the other room. This is a function generator, and what it's doing is it's producing a voltage function at a frequency shown here at about 927.28 hertz, around there. And that voltage is connecting into this channel here and displaying on the screen here. And there's some mechanisms on the inside of the oscilloscope that are turning this voltage into this sinusoid. So I think we should pop this open and Nathan can talk about that.
Okay, Nathan, so what's going on with this oscilloscope now that we have it open?
This is the inside of the oscilloscope, and we have a diagram here that pretty much represents what is inside of this area that we can't really see. So at one end of the oscilloscope, there is a filament that, when it's heated up, will boil off electrons that, and the electrons then go through a potential difference that accelerates them, it accelerates them across this potential difference towards this area with the steering plates. And whenever a voltage difference is put across these plates, that will steer the electron beam either up or down through these vertical plates, or left and right through these horizontal plates. And however that the electron beam is directed by these four plates will then determine where it lands on the screen, and that electron beam will then fluoresce with the phosphorus coating on the screen and illuminate.
And that's the spot we see.
Yes, that is the spot we see.
So how does the electron beam, how do we see that sine wave? How does it create that sine wave?
So inside of the oscilloscope, there is a circuit that applies a voltage difference across the horizontal plates that repeatedly sweeps the electron beam across the screen.
So if there's no voltage across the vertical plates, then we would just see like a straight line.
Yeah, so it would just be a straight line across.
So then now when we have a voltage across the vertical plates, what happens?
So the function generator creates a voltage difference across the vertical plates in a similar manner to the horizontal plates, but it oscillates up and down very quickly, and that mixed with the constant horizontal motion of the beam across the horizontal plates creates this sine wave. So it's the rapid and consistent horizontal motion from left to right, and the oscillating vertical motion up and down. So that creates a sine wave.
The voltage signal across the function generator is placed directly across the steering plates, pretty much, right? And that controls, it seems like that's going to control the vertical steering. Cool, that's pretty amazing. So this is like totally analog. There's nothing digital about this.
Yep.
It's literally electrons getting steered by electric fields across these plates, in between these plates. Mm-hmm. Pretty amazing.
One way to steer the electron beam is to change the electric field inside the oscilloscope. Another way to do this is to use a magnet instead. Picture on the screen shows a U-shaped magnet brought near the oscilloscope, seen from above. Left side of the magnet is the magnetic south as labeled on the magnet, and the right side is the magnetic north. Therefore, the magnetic field line comes out of the right side and loops back into the left side, and at the oscilloscope screen, the field points to the left. Charged particles in motion, such as the electron beam, experience a force under the influence of magnetic field. This force is given by the following formula: F equals Q times V cross B. In order to find the direction of the force, we need to calculate the cross product. To do this, take your right hand and point it in the direction of the velocity vector. While you do this, have your palm face the direction of the magnetic field vector. And lastly, hold your thumb perpendicular to the other fingers, and this gives you the direction of the cross product, V cross B. However, because electrons are negatively charged, Q is negative, and therefore the direction of the force is the opposite of that of the cross product. Therefore, in this picture, the force should point upward, and the magnet should steer the beam upward.
So if this really was an electron beam, then electrons are, since they're negatively charged, and if they're in motion, if we were to bring this magnet closer, according to the Lorentz force law, the beam should move a little bit upwards or downwards, depending on the orientation of the magnet. And let's try to do that with this magnet. The north side is on the right side and south side is on the left side. Just trying to match the diagram I drew earlier, and let's try to bring it closer. And then it does indeed move upwards, which suggests that, as expected from the calculation, that this beam is a negatively charged particle in motion.
Cool. So what happens if you turn the magnet?
Now I'm having the south side on the right side. And the beam moves downwards, opposite of what it was before.
We're steering the electron beam
Yeah.
with a magnetic field. Awesome.